This video is going to be focusing on learning target 1.4, how to describe the relationship among wave speed, frequency, and wavelength of mechanical waves, otherwise known as aeromath. This video is going to be using the CER statement and using the wave on a string simulator for examples. It assumes that you already know how to do aeromath with the wave equation. For example, if frequency is constant and the wave speed goes up, we know that the wavelength also has to go up to keep both sides equal. And it also assumes you went through claim, evidence, and reasoning, and you know what a claim, evidence, reasoning statement is. So first I'm going to be using this other simulator that we used earlier. I opened this up here. So going to this one, we can see our first wave is 0.567 hertz, 177 centimeters, and 100 centimeters per second. So going back to this, you can see I have 0.568 hertz, which is pretty close. The speed is 100 centimeters per second, and the wavelength is about 177 centimeters. So this is the first wave right here, the starting wave, and it looks like this. Now it says change your frequency to 0.054 hertz. 0.054 hertz. So I'm gonna go to here. I'm gonna go 0.054. That's down. 0.2, 0.1, 0.0056 is as close as I can get. 0.056. Oh, look at that. Look what happened to the waves. They got really long. Okay, so 1785 centimeters. 1785 centimeters, and the speed should still be the same because I didn't change the speed. It's 100 centimeters per second. So here's my second wave, 0.054 hertz, 1785 centimeters, 100 centimeters per second, and 2 centimeters. Now we have to do our aeromath, and I'm looking at this, I'm seeing frequency is going from 0.5 to 0.05, so frequency is going up or down. It's going down. So I'm going here, show frequency going down, save that. And then it says wavelength is 177 to 1785. So wavelength is going up. Wavelength is going up, lambda. Wavelength is going up. So save that. And the wave speed is staying 100. So go back to here, and wave speed is staying 100. And I don't need these anymore. So there's my arrows, my aeromath. Now I have to type out my claim, evidence, and reasoning. So first, the claim answers the question or the prompt in a complete sentence. So we have to answer the question. Going back here, what type of proportionality, inversely or directly? I'm looking up here, and I see frequency is going down and wavelength is going up. So they're going in opposite directions. Opposite direction is like inversely proportional. So my claim is going to be like this. My claim is going to be that frequency and wavelength are inversely proportional. That's my claim. Answered the question. Now I got to do the evidence. The evidence identifies what data is used to support your claim. So this has to focus on the data. So the data is going to be in our data table. And what we're noticing is frequency and wavelength are inversely proportional, so that's what we want to focus on, the frequency. The frequency goes from 0.567 to 0.054. Frequency goes from 0.567 to 0.054. The wavelength goes from 177 centimeters to 1785 centimeters. All right, now the last part is the reasoning. So the reasoning has two parts. Describe how the evidence supports a claim and the scientific principle. So how does the evidence support the claim? Well, the evidence supports the claim because, well, this is part. Just say frequency is decreasing while wavelength is increasing. They are going in opposite directions. So they're inversely proportional. And then the second part, describe the scientific principle. So here's where we have to use our aeromath. We already figured it out here. I want to be able to put it in here like this. Okay. We can see that frequency and wavelength are inversely proportional using the wave equation. And so I'm going to paste this here. And what we have, velocity is staying constant, frequency is decreasing. So this one goes like this. And wavelength is increasing. So come on, copy that and paste it there. So there's my complete assignment, inversely proportional. Claim, evidence, and reasoning. Now we're going to do the same thing, but this time using the wave on the string simulator. So open up my lab file and click here, wave on the string, and there it is. And then the first step says, use the image to correctly set up the simulation. And then it says the black arrows are pointing at different things. There's black arrows here, 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 and there. They're showing the settings like oscillate and no end. So let's do oscillate and no end. Let's do those. Here you go. So oscillate. There you go. I'll get oscillate and no end. Going back to here, got those done. Dampening equals none. So that's right here, dampening. Dampening is on none. So go back to here and dampening goes to none like that. And then it says tension equals high. High tension. Tension's here, it's on high. Back on here, tension is, it's already on high. And then back to here, and it says rulers box is checked. Rulers box. So back to here, turn on my rulers. So now I'm set. Okay, so let's set this up. Our first wave is right here. 1.25 hertz, 6.12 centimeters per second. So wave on the string. 1.25 hertz. So that'll be 1.25 hertz. Okay, and then I'm going to pause it and move my ruler and then get the wavelength from crest to crest. It goes 1, 2, 3, 4, 5 centimeters, 5 centimeters. And that's what it has. 5 centimeters, 1.25 hertz, 5 centimeters. And the wave speed is already filled out for me. I think we get that with the wave equation just by multiplying these two together. Now it says change the frequency to 1.5 hertz and observe for 15 seconds. Okay, so back to here. Hit play. 1.5 hertz now. So 1.5 hertz, like that. Observing it. The waves look a little different. Okay. Now record the data below. You need to pause the waves and measure the wavelength using the ruler. So back to here. Pause. Pause. And take the ruler and put it right on top. Like that. And it goes crest to crest. So 1, 2, 3, 4.2, 4.1, 4.2. I'll call that 4.2 centimeters. 4.2 centimeters. And the wave speed's there. So there's our data. How do the waves look different? Identify, highlight at least 2 observations. So when it was a lower frequency, the waves were longer. So now they're shorter. The waves look shorter. All right, now I gotta do the arrow math. Okay. Frequency goes 1.25 to 1.5. So frequency is increasing. And then wavelength goes 5 to 4. So wavelength is going down. And then speed is 6.12 and 6.12. So speed is staying the same. Oh, so I don't need these. And there's my arrow math. Now we gotta do claim, evidence, and reasoning. What type of proportionality and type my claim, evidence, reasoning. All right, I'm looking at this and what do I see? for proportionality, inverse or directly proportional. So the claim answers the question, and I saw these look like they're opposite, so inversely proportional. Frequency and wavelength are inversely proportional. Now the evidence. Evidence is the data. Evidence has to do with the data. So going back to my data, and now I'm going to describe my data. Frequency and wavelength. Frequency goes from 1.25 to 1.5. And wavelength goes from 5 to 4.2. So that's my evidence. And now the reasoning. Remember, reasoning has two parts. First part is describe the evidence, and then the scientific principle. So the evidence is as frequency increases, the wavelength decreases. Which, since one's going up, the other one's going down, they go in opposite directions. So they're inversely proportional. And then the final part is describe the scientific principle. The scientific principle. So we have to go back to our wave equation. We already wrote the wave equation up here. And I think I want to grab these again so I can use them for my explanation. The wave equation shows that frequency and wavelength are inversely proportional. And here's my wave equation. And it shows frequency going up and wavelength going down. So yeah, and speed is constant, just like that. There you go.